In this video, we're solving problem 12.1.004 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the domain of a vector-valued function and enter our answer using interval notation. So we've got a vector-valued function like this. This is our x component. We've been calling it x of t. And this is our y component. Call that y of t, and that's our z component. We'll call it z of t. And remember how this works. For every value t in the domain of this function, we're going to map to a point in three-dimensional space, and the location of that point will be at x of t, y of t, z of t. So just to make a cartoon of how this works in general, there's no t-axis here. We've got the x-axis, the y-axis, and the z-axis. But for every value of t in the domain of this, we're going to map to some point in three-dimensional space. Now, r of t is just a pointer. It points at a particular location. Most of the time when we graph a vector-valued function like this, we just graph the end point. We just graph x of t, y of t, z of t, and think about what would happen as t increases, almost as if this is a position function. So at a certain time, we might have a particle that's at this location, and then later at this location, and then later at this location. And as t increases, we just trace out that curve in three-dimensional space. And r of t, again, is a pointer. It starts at the origin and it points right here. And that location is x of t, y of t, z of t. So that's what this represents. Now we're trying to find all of the values of t that we can plug into this function over here where the answer that comes out will make sense. I'm going to use component form rather than this standard unit vector notation. So I'll use this form instead. Finding the domain of a vector-valued function is actually pretty simple. It's the same as finding the domain of this function of a real variable and this function of a real variable and this function of a real variable. So you find the domain of each piece. And then you need to find out where all of, well, those three domains, those are going to be intervals or potentially unions of intervals. You want to find out where those intervals overlap. That's called the intersection. So the way we start this problem is we find the domain of this guy and the domain of this guy and the domain of this guy, and then we find out where they overlap, which is called the intersection. So first I'll find the domain of x of t. Now this is what you have to remember from pre-calculus. The values of t that will work here and here and here are the values of t that we can put in that aren't going to cause any problems. So we want to exclude values of t that cause the following problems. Any other value of t will be fine. So we want to exclude values of t that cause division by 0, because we know we're not allowed to divide by 0. We want to exclude values of t that cause even roots of negative numbers. So a square root of a negative, a fourth root of a negative, a sixth root of a negative, all of those are going to be complex numbers. And that would be fine if the output were supposed to be complex, but these are supposed to be real outputs. That's a real number x of t, and a real number y of t, and a real number z of t. So we can't take even roots of negative numbers if we want real numbers to come out of this. And lastly, we can't take the logarithm of a negative number or 0. So we want to exclude values of t that cause logarithms of negative numbers or 0. So we can't take the log of 0, and the log of a negative actually turns out to be a complex number as well. Okay, so the domain of x of t is probably the most interesting of these three components because it's the only one that has any of these problem issues. So I'm trying to find the domain of this square root function. And I don't have to worry about division by 0 because there's no division. And I don't have to worry about logarithms of negative numbers or 0 because there's no logs. But I can't take the even root of a negative number. So that means the domain is going to be the set of all real numbers t, such that this expression under the radical, so that's the number inside that square root, is greater than or equal to 0. So that means I need, if I add t squared to both sides, t squared, or 36 to be greater than or equal to t squared. Or I'll just change the order. It's t squared has to be less than or equal to 36. Now this is actually one that's a little bit hard for students to wrap their minds around sometimes. I find that it's easier if you think of this visually. Think of this as a function, y equals 36. And think of this as a different function, y equals t squared. The question is, when is this t squared function less than this y equals 36 function? Or in other words, graphically, when is this y equals t squared parabola below the graph of the y equals 36? Well, I think we can all see that it's below that line from here to here. The parabola is below the line right there. And we're looking for a set of t values where that happens. Well, I know that t squared is equal to 36 when t equals plus or minus 6. So it looks like t squared is going to be less than or equal to 36 on the interval from -6 to 6. And it actually says less than or equal to, so those points are included as well. So the domain of this guy is the solution of this inequality, which is the set of all real numbers t such that t is between -6 and 6, but they want interval notation. So it's the interval from -6 to 6. So that's the domain of x of t. When we're finding the domain of y of t, we're just finding the domain of t squared. We have to get rid of any t values that cause division by 0. There's no division, so we don't have to worry about it. Any t values that cause even roots of negative numbers, we don't have any even roots, so we're good. And logs of negative numbers are 0. There are no logs here. So what that means is I can put in any t value I want, any real number t, and I can square it, and that's going to be just fine. So the domain of this guy is all real numbers. You can write it as the r with the double bars, or you can write it as the interval from -infinity to infinity. Since there's no division, there are no even roots, and there are no logarithms. It's just all real numbers. And the domain of z of t, in this case, z of t is -7t, or in this form, you have the -7t in front of the k hat there. Can you take any real number and multiply it by -7 and get a real number back? You sure can. So the domain of that guy is all real numbers. Now, when we talk about the domain of r of t, we need t values that work for x, y, and z. So if x were, say, or excuse me, if t were, say, -7, I couldn't put it into this function. So if I take -7 and I square it, I get 49, and I have 36 minus 49. Well, it's a negative number, and I'm not allowed to take the square root of a negative number. Not in the real number system, and we want all of these guys to be real numbers. So since t equals -7 isn't in this one, it can't be in the domain of r of t. We need all the t values that are in this set, and in this set, and in this set. Or if I graph them, this is the interval from -6 to 6, and all real numbers, and all real numbers. I'm looking for the set of t values where those three intervals overlap. I think we can see that they all overlap right here, from t equals -6 to t equals +6. That sense of overlapping is called the intersection of those three sets. So the domain of R of t is the intersection of the domain of x and the domain of y. These are x of t and y of t, and the domain of z of t. Just dropping that dependence on t, even though we really know that those three depend on t. And that little upside down looking, it looks like an upside down U, excuse me, that means intersection. And again, that just means I'm looking for this set of t values that is in this set and this set and this set. Well, those t values are fine in these two sets, but they're not in this one. But once I get between -6 and 6, all of those are in all three sets. But once I go past 6, I'm in trouble again. The t values are in the domain for y of t and z of t, but they're not in the domain for x of t. So the set of t values where all of these guys overlap is a set of all real numbers t such that t is between -6 and 6, which can be written in interval notation, as that interval from -6 to 6 include the square brackets because both endpoints are included.